All right, let's dive right into this explainer. Today, we're taking a journey from the runway all the way to the edge of space to decode the sky above us. You know, when we look up, we usually just see empty blue space or some passing clouds. But for pilots and meteorologists, the sky is this highly structured, layered, and strictly mathematically defined environment. So we're going to break down the exact composition of our atmosphere, the vertical layers that define it, and those absolutely crucial international standards that keep global aviation safe every single day.
Think about it. It's actually a massive puzzle. If atmospheric pressure and temperature are literally always shifting with the weather, changing from day to night, summer to winter, how in the world do planes avoid flying into terrain, or worse, each other? How does a pilot flying over Tokyo and a pilot flying over New York make sure they are using the exact same invisible ruler to measure their distance from the ground?
So here is our flight plan for today. 1. Our atmospheric recipe. 2. Journey through the layers. 3. The tropopause boundary. 4. The standard atmosphere. And 5. Why the baseline matters.
Okay, kicking things off with part 1, our atmospheric recipe. What exactly are we flying through?
Let's start with the absolute basics of our environment and look at the actual chemical makeup of the air wrapping our planet. When you take off, what's out there? Well, up to about 80 kilometers in altitude, which is a boundary scientists call the homopause, the air is surprisingly uniform. It is heavily dominated by nitrogen at 78% and oxygen at 21%. That right there accounts for 99% of the air we breathe and literally the air that generates the lift over an airplane's wings.
But we absolutely cannot ignore the leftovers. While that 1% of trace gases seems like a tiny drop in the bucket, things like carbon dioxide and water vapor act as our primary greenhouse gases. They fundamentally drive the thermal energy of our lower atmosphere by trapping long-wave terrestrial radiation. Honestly, without this tiny fraction of trace gases, our lower atmosphere just wouldn't be warm or habitable. The weather as we know it simply wouldn't exist.
Moving right along to part 2, Journey Through the Layers. Let's ascend to the edge of space.
Imagine you're in an aircraft, climbing out of the airport and moving vertically through these distinct concentric layers of the Earth's atmosphere. Now, these layers aren't separated by physical walls, right? They're defined by how their temperature changes as you go up. We start in the troposphere. This is where 80% of the entire atmospheric mass and virtually all the moisture lives. It's heated from the bottom up by the Earth, so the temperature drops as you climb. It's bumpy, turbulent, and full of weather. Just above that is the stratosphere, going up to about 50 kilometers. Here, we actually get a temperature inversion. It gets warmer as you go up because the ozone layer is busy absorbing solar UV radiation, making the stratosphere highly stable and totally free from convective weather. Keep going and you hit the mesosphere with plunging, freezing temperatures, and finally the thermosphere, where high-energy solar radiation makes the temperatures absolutely spike again. Now, for commercial aviation, pretty much all the action happens in the troposphere and just the very lower edges of the stratosphere.
Which brings us to part 3, the tropopause boundary, the literal ceiling of our weather.
So the transition between those two lowest layers, from the turbulent troposphere into the smooth stratosphere, we have to hit a critical ceiling. This ceiling is vital for aircraft performance. And what's really fascinating here is how thermal expansion drastically changes the height of this boundary depending on where you are on Earth. Since its height is directly tied to surface temperature, it's definitely not a perfect sphere. At the hot equator, strong thermal expansion pushes the tropopause way up to about 16 to 18 kilometers, or roughly 54,000 feet. But over at the freezing poles, the dense, cold air drags that ceiling down to just 8 to 10 kilometers, or about 28,000 feet. And because of these massive differences in height, it's not a smooth shell at all. The tropopause is actually discontinuous. It literally fractures at specific latitudes, usually right around 30 degrees and 60 degrees. And guess what? These fractures are exactly where we find those powerful jet streams whipping around the globe, creating these high-speed corridors of air that airlines ride to cross oceans way faster.
All right, part 4, the standard atmosphere, bringing some math to a chaotic sky. We have just seen how wildly the real atmosphere varies by latitude, by season, even by the time of day. So the big question is, if the real sky is always changing its temperatures and its boundaries, how on earth do we standardize aircraft altimeters worldwide? If an altimeter uses air pressure to guess its altitude, a chaotic atmosphere is a massive problem. Well, the solution is the ISA, the International Standard Atmosphere.
We basically just replaced the messy reality of meteorology with a perfect, unchanging mathematical model of how pressure, temperature, and density change as you climb. It gives every aircraft in the sky a uniform global reference.
To build this mathematical model, the ISA sets its absolute baseline right at mean sea level. It starts with a perfectly standardized sea level temperature of exactly 15 degrees Celsius.
And then it pairs that 15 degrees with a standard sea level pressure of exactly 1013.25 hectopascals or millibars. This number right here is the bedrock of global aviation altimetry.
From that baseline, aviation relies on these incredibly handy rules of thumb. Within this ISA model, as you climb, the temperature drops roughly 2 degrees Celsius for every 1,000 feet. Atmospheric pressure drops 1 hectopascal for every 30 feet of altitude you gain in the lower troposphere, and mathematically, the ISA just locks the tropopause at exactly 11 kilometers, where the temperature stops dropping and holds steady at minus 56.5 degrees Celsius. This beautifully clean math lets pilots and flight computers instantly calculate what the atmospheric conditions should be at any altitude.
Finally, Part 5. Why the baseline matters. Let's talk about applied altimetry for safe skies.
Let's see how all of this builds into real-world, in-the-cockpit decision-making. We've got our chaotic real-world weather, and we've got our perfect ISA mathematical model. How do we safely reconcile the two? It all starts with the concept of the flight level. When aircraft are cruising high up, above what we call the transition altitude, every single pilot stops using local, real-world pressure settings. Instead, they all dial their altimeters to that ISA standard, 1013.25. By forcing everyone onto this exact same standard pressure datum, your actual height from the ground might be slightly off because of the weather, but every aircraft is using the exact same baseline ruler, and that elegantly guarantees safe vertical separation between traffic.
But we aren't always flying way up high in the sky. What happens near the ground, say during an instrument approach through mountains, when the real-world temperature is much, much colder than that standard 15 degrees Celsius? Flying in weather colder than the ISA model actually introduces a terrifying hidden danger. Let's work through exactly why extreme cold is so dangerous. Step 1. Cold air is significantly denser than standard air. Step 2. Because it's denser, atmospheric pressure drops way more rapidly with altitude than the ISA model expects it to. Step 3. Your barometric altimeter, which is just dumbly measuring pressure, gets tricked. It overreads. Step 4. The result? Your true altitude is actually lower than your indicated altitude. Your instrument panel might say you're at 5,000 feet, supposedly clear of a mountain peak, but in reality, you might be hundreds of feet lower. This puts you at severe risk of what aviation calls CFIT, controlled flight into terrain.
This is exactly why pilots absolutely cannot just blindly trust their instruments in extreme cold. They have to mathematically correct their minimum approach altitudes. The rule of thumb here is a 4-foot altitude correction for every degree Celsius the temperature drops below the standard ISA per 1,000 feet of altitude. Aviation authorities worldwide like ICAO mandate these corrections to prevent CFIT. It just brilliantly illustrates that understanding the physical structure and the math of our atmosphere isn't just trivia, it's quite literally a matter of life and death. So we've gone from the raw nitrogen and oxygen in the air, up through the fractured tropopause, right down to the life-saving mathematics of the ISA altimetry model. The sky isn't just empty air, is it? It's a highly structured, intensely mathematical environment that keeps us safe every single time we fly. So the next time you look out of an airplane window, will you just see clouds, or will you see the invisible architecture of physics working all around you? Thank you so much for joining me on this explainer. Keep looking up and keep learning.